Okay, I think we'll get started. So today we're going to talk about intermolecular forces. So these are non-specific forces that occur between molecules. There's a bit that's an attractive piece, and then if the molecules get too close together, there's a repulsive piece. Now, before we start, let's talk a little bit about polarization. We've mentioned it as well. We'll only mention it a little bit here. We haven't laid down the idea formally of an electric field yet, so we won't talk about this in complete detail. Polarization will be occurring through the rest of the course in various places. But basically, if we've got a molecule that isn't necessarily polar, in fact, it's most helpful to think about a nonpolar molecule. It's got its electron distribution around the nuclei based on however the atoms come together. Now, if we put this in the presence of a charge, the electrons will respond by being attracted towards positive charge or repelled from negative charge, and that can distort the electron cloud around this molecule. And so it polarizes, and that can induce a dipole. So this is an induced dipole. If it's a single charge, an ion, then we call it an ion-induced dipole. If it's a dipole, then we would call it a dipole-induced dipole. All right, well, so what are the forces in play in a liquid, solid, gas even, but gases molecules are spending most of their time away from each other, and only very rarely are they colliding. In a liquid, they're typically colliding every 15 to 20 femtoseconds, and they're always in interaction with to some degree with their nearest neighbors. And so let's talk about the forces and the potential energy of interaction for these. Well, we've already done a few. We've done the ion-ion. That's, of course, just Coulomb's law. So what I'm going to do here is just denote the functional behavior of the force with distance. So we know the Coulomb force falls off as r squared. It could be positive or negative. Right? If it's attractive, then the ions will want to come together. If it's repulsive, they'll want to move apart. The potential energy is always the integral of the negative integral of the force. I'm not going to include minus signs in here. We're just looking at the functional form of the distance. So it's a 1 over r potential for the potential energy. The ion dipole, we worked that out carefully, and we got a 1 over 3 r to the third. 1 over r to the third force, and then of course the potential will be 1 over r squared. Now, beyond that, beyond these Coulomb forces, we get into what are called the van der Waals forces, and the strongest of these, or the longest range of these, are the dipole-dipole interaction. And so it's a complicated calculation, although it's doable. But when you do it, you see that the force drops off as r to the 4th power, and thus the potential energy drops off as r to the 3rd power. Here's an example here of an ion-induced dipole, and the force there drops off as 1 over r to the 5th power. This is a very weak force. Well, not necessarily weak, but short range. So it's getting shorter and shorter range as we come down here. The interaction, the potential energy, is 1 over r to the 4th then. Then we get into a whole set of 1 over r to the 6th potential energies, or 1 over r to the 7th forces. The first of which is a dipole-induced dipole, and the second of which is a dipole-dipole, but different than this. What's happening here is we're doing a cycle, a thermally averaged dipole, and we find that So we know the dipole, if it was just totally averaging, if this was spinning really quickly relative to this dipole, then everything would average out and we would just get zero force. But there's some attraction there. It's a little lower in energy if the two are lined up well, and then higher in energy if they're lined up opposite. And so when we're at temperature, this is moving around and it's spending a little more time lined up correctly than incorrectly. So we do get an attractive force there. This is called the Keesom force, and it's of the form 1 over r to the 6th in the potential energy. Then we have dipole-induced dipole. So this would be like if a polar molecule is adjacent to a nonpolar molecule. And then, interestingly, we can get what is called dipole-induced dipole. And I like to tell the students, think of it kind of as spontaneous dipole induces a dipole through a dipole-induced dipole interaction. And then that induced dipole back stabilizes this. So through fluctuations in where the electrons are, there'll be these transient dipole moments to these nonpolar molecules. And because there's a molecule next to them, that molecule's electrons will respond in a way that favorably stabilizes the original dipole. And although that's weak and very short-ranged, it's a significant, and it's why nonpolar molecules can actually condense into a liquid. So take something like carbon tetrachloride is a liquid at room temperature. And the reason it is because of the intermolecular force of induced dipole. These are also referred to as London dispersion forces, and they drop off also as r to the 6th. So if we sketch the potential energy that one molecule feels compared to another, a good model for that is something called the Lennard-Jones potential. Of course, there's a whole bunch of other potentials. The Lennard-Jones is sometimes called the 6-12 or the 12-6 potential, and it's of the form 1 over r to the 6th. So that's representing these van der Waals forces of the 1 over r to the 6th type. And then there's the internal core. So it's not a hard core. It's a soft core, but it's pretty steep. It's r to the 12th. So this just goes off very quickly to infinity as you try to squeeze the two molecules too close together. So there's an optimal distance based on the different types of van der Waals forces for the molecule to sit. It's not a chemical bond. There's no directionality to it, but yet it's still an attractive force. And it gives rise to liquids in nonpolar molecules, for example. Now, the last thing that we'll talk about here, and we're actually going to break this out into two separate videos, are the specific interactions. Now, these are very important, in fact, critical for life important, intermolecular interactions, but they're distinct in these. They're directional. They have characteristics that aren't as generic as the van der Waals forces. They can be much stronger. They can be much weaker than these forces. The two that we are going to focus on are hydrogen bond, and this is essential for all sorts of things in biology, in different material science. Everywhere we see hydrogen bonding. Halogen bonding is related to hydrogen bonding, and it serves as a neat other example. So when you look in your book on specific interactions for intermolecular forces, there's only just hydrogen bonding. So you might wonder, well, what else is there? And so halogen bonding is a good extra example for that. Then there are other things we won't talk about, but you will talk about that if you end up taking a course in organic chemistry or some kind of synthetic chemistry. And that's a pi-pi interaction, so pi bonding orbitals can interact with each other. And there are other specific interactions as well that are really quite specialized in terms of what physical chemists study. All right, so this is a brief kind of discussion of intermolecular forces. And really they are electrostatic in origin. Now these, particularly the induced dipole, they're inherently quantum mechanical. And so we would have to have a course on quantum mechanics, which is definitely we'll have several courses on quantum mechanics in the curriculum, but we aren't ready to talk about just how this happens yet, other than our sort of hand-wavy way that I talked about earlier. But at the end of the day, it's all inherently electrostatic. It's because charges are present, and charges can move around and be polarized.